So now we will spend some time and understand the difference between 1-2 addition and conjugate addition, and how the reaction conditions can actually dictate the outcome of the reaction. Okay, so now let's go back to the first reaction that we sort of looked at in the beginning of this lecture. So you start with this compound, and when you add NaCN, HCN at somewhere between 5 and 10 degrees centigrade versus the similar reaction conditions, that is NaCN, HCN. The only difference is we do this reaction at 80 degrees centigrade. Okay, so the product that is formed in the first case is the cyanohydrin. Okay, and the product that is formed in the second case is the addition to olefin. Okay, so now the question that we are all trying to understand here is, these are experimental facts and they are very well established, and the question that we are trying to address here is, how do we explain this result? Okay, now so I would urge all of you to pay a little bit of attention over here so that we can see if everybody understands this concept. Okay, so what is proposed is that when you start with this type of a carbonyl compound, and when you add a CN minus, okay, so we have looked at already the formation of cyanohydrin. So you can produce this kind of an intermediate, which can then pick up a proton and give you the product. Okay, now at 5 to 10 degrees centigrade, this is the dominant path. That means that you don't see the other product being formed. We also know that if you take cyanohydrins and dissolve them in just an organic solvent, we also know that this can go back. That is, you can get back this compound plus cyanide. Okay, so this is something that we already know from our previous discussions, and so therefore the formation of cyanohydrin is a reversible reaction. Okay, which means that it is going to be in equilibrium, right? So as in when you add cyanide, you're going to form this product, and then you work up the reaction and you will be getting this as the product. And now when you dissolve this in an organic solvent, it is possible that you will get some of the starting material back and cyanide back. Okay, so therefore what we can understand, or what we can suggest, is that the first step here is a fast, given the outcome of this reaction, we can suggest that the first step is a fast reaction. However, it is also a reversible reaction. So I guess we've already written it over here. So it is a reversible reaction and it is a fast reaction. Okay, so this helps us understand what happens at somewhere between 5 and 10 degrees. Okay, and we also know that it is reversible. Now the importance of reversibility will come now, because at 80 degrees centigrade, when we carry out this reaction, right, so now the product that is formed is actually the conjugate addition product. Okay, now what we can suggest is that, based on the observation, that this must be a slow reaction. Okay, because at somewhere between 5 and 10 degrees centigrade, you do not observe this product, but you need a higher temperature, which likely means that you need a larger fraction of molecules which have enough energy to get over the barrier to form this product. Okay, so I will now just quickly summarize. So what we are suggesting is that at 5 degrees or low temperatures, somewhere between 5 and 10 degrees centigrade, this reaction gives you Cn, OH, and a double bond. Okay, so this is the fast reaction. Okay, compared with this, because the conjugate addition does not occur at 5 to 10 degrees centigrade. So therefore, the conjugate addition must be a slow reaction. Now, the slow and fast is again going to be a relative term. So the formation of the cyanohydrin must be a fast step. Now, why is the equilibrium important? Because even at 80 degrees centigrade, this fast reaction will be the dominant reaction. So it is not that the reaction is not going to occur at 80 degrees centigrade. This reaction will occur at 80 degrees centigrade. The only suggestion here is that it's going to be a reversible process. Okay. Now I will just go through quickly the energy profile so that you will understand this process better. So y-axis is energy and the x-axis is reaction coordinate. So what we can look at is, let's start with this compound over here. This is the starting material. Okay, and now what we are suggesting is that the first step of this reaction must have some barrier, and you get O minus Cn and this product. Okay, and then subsequently this is going to give you the product, and I'm just going to assume that it's an exothermic reaction, and this is just a protonation step, so therefore this would give you Cn OH CH3. Okay, so let me just redraw this barrier so that it's a little bit more reasonable. Okay, now this is fairly straightforward. Now the important point here is that the first step that's going to be, that is reaction with cyanide, can occur, and there's enough energy that is at 5 to 10 degrees for this reaction to occur. Now, since the conjugate addition is the slow step, it's likely that the barrier for conjugate addition must be higher. Now, again, this is basic kinetics. A slow reaction means that the barrier would be higher, and the fast reaction means the barrier would be lower. Again, we are comparing the same molecule reacting, that is, this molecule reacts with cyanide, so all the reactants are identical. The only difference here is the products that are formed. Okay, so it's likely that this barrier, that is EA, for the first reaction, and this is the energy of activation for the second reaction. So it is quite likely that EA, or it is obvious that EA1 is lower than EA2. Okay, and this we can clearly reason out because at 5 to 10 degrees centigrade there is no reaction, or there is no conjugate addition that is actually happening. Now this is the product that is going to be produced, so that is going to be formed, and so here is the, let me just erase this part so that I'll draw it a little bit better. Okay, now so this is the conjugate addition product, and then this is going to subsequently pick up a proton and give you the product. Okay, so here is the initial intermediate, the enolate O minus, and the final product is the conjugate addition product. All right, so now the important point here is that this EA2 is going to be greater than EA1. Okay, Now, here's the question about reversibility. So, when you look at a reversible reaction, what it means is that the barrier for the reverse reaction, that is, barrier for this reaction, is going to be accessible at the temperature at which you're doing the reaction. Okay, so when we look at the formation of a cyanohydrin, we know that it is reversible. So, therefore, the barriers of the forward reaction as well as the reverse reaction are actually accessible at the temperature at which you do the reaction. Even more so, there's a larger fraction of molecules which can cross the barrier. Even more so, at 80 degrees centigrade, this reaction is going to be happening at a substantial rate. However, in order to explain the formation or this result, we have to invoke the concept that the last reaction, which is the formation of this conjugate addition product, is an irreversible reaction. Okay, so that means that this barrier EA reversible for conjugate addition is very high. So I will just go through this once again in a fresh slide so that you understand this better. I'm just going to remove all the structures and just explain to you what this concept is. Okay, so I have a starting material. Okay, and I'm just going to simplify this by drawing out two products. So this is going to give me P1 and this is going to give me P2. Okay, so the way this is constructed is that this is EA1 and this is EA2. So the first concept here is that EA1 is less than EA2. Okay, what this tells me is that the formation of P1 is substantially faster when compared to the formation of P2. And the second concept is that the formation of P1 is reversible. And this helps us understand the why a particular product is actually not formed at higher temperatures. So just to be clear here, if EA1 is less than EA2, no matter what the temperature is, okay, the product 1 is going to be formed much faster than P2. There is absolutely no doubt about this. That is, if this barrier is lower than this barrier, P1 is always going to be formed faster than P2. Okay, but since P1 formation is a reversible reaction, that means that this barrier is accessible at the temperatures at which we are doing this reaction, or as a larger fraction of molecules have enough energy to cross this barrier, it goes back to forming the starting material. Okay, and then since there is a fraction of molecules, for example, at 5 to 10 degrees, the largest fraction of molecules can only go back this way. This goes back here and forms P1. But at 80 degrees centigrade, this is a reversible reaction. That means that this goes this way, gives you back the starting materials, and then the starting materials can cross this barrier and give you P2. Okay. Now, the only way in which we can explain this reaction, or one of the ways in which we can explain the formation of these products, is that the reverse reaction, that is, the reaction of P2 going back to starting materials, has an extremely high barrier. So if you look at this, this is the barrier that we're looking at. And this barrier is inaccessible at 80 degrees centigrade. And therefore, this reaction is irreversible reaction. Okay, and this helps us explain the distribution of products at two different temperatures. So the 1,2 addition product is actually formed much faster when compared to the 1,4 addition product. But since the 1,2 addition product is actually less stable, so if you see there's a difference in the energies of these two. and P2 is definitely more stable than P1. And since the 1,2 addition product is actually a reversible reaction, this reverses and goes back to producing the starting materials. And then the starting materials, there is a larger fraction of, or a fairly large fraction of molecules which can actually cross this barrier and give you P2. But now, once they form P2, they don't have enough energy. P2 doesn't have enough energy to come back to the starting materials, and therefore, this reaction goes in this direction at 80 degrees centigrade. So, this is a very important concept that all of you have to understand. Now, I'm going to use some terminologies here for us to put in perspective. Okay. So, when you have this kind of a situation where you have a starting material and giving you P1 and starting material giving you P2, and let's say the formation of P1 is much faster than formation of P2, these types of products are called the kinetic products. That means that the outcome of the reaction is dictated exclusively by the rate of formation of the product, and the major product that is produced is actually the kinetic product. So if you recall, if I look at the barriers, energy versus reaction coordinate, I have this, and I'm going to give you this product, and this is P1, this is the starting material, and the formation of P1 is substantially lower in energy compared to the formation of P2. Okay, so therefore this compound, that is the product 1, is called the kinetic product. Now P2 is invariably never formed if P1, if this doesn't reverse. So if this is an irreversible reaction, that is, if there is a competition between the formation of P1 and P2, even if you go to higher temperatures, P1 is only going to be the major product, unless it is a reversible reaction. So if it is a reversible reaction, that means if this reaction can also go in this direction, then the starting materials are formed again, and they're going to give you back P2. Okay, and this kind of a product is called the thermodynamic product. Okay, and this thermodynamic product is usually fairly more stable compared to the kinetic product. Okay, so I will repeat here. When you have a competition between two different products, the formation of two different products, the one which has the lower barrier will always be formed at a higher rate. Or to put it in a different way, the major product that is formed, the interpretation from that result is that the barrier towards the formation of that product is lower. And there may be a minor product that is formed, which is P2 at lower temperatures. And the formation of P2 is always going to be slower compared to P1. So now when I increase the temperature, what is going to happen is that a larger fraction of molecules have higher energy. And now when a larger fraction of molecules have higher energy, P1 is still going to be the major product. That means P1 is going to be formed much faster when compared to P2. However, if the formation of P1 is reversible, then this reverse reaction can occur, give you back the starting materials, and those can again react and give you P2. Now, if P2 is an irreversible reaction, that means that the reverse reaction does not occur, then P2 ends up becoming the major product. And P1 is called the kinetic product, and P2 is called the thermodynamic product.